Thanks for coming, everyone. I'm going to be talking about scaling library workspaces. And this is going to be an experience talk, sharing some learnings from just maintaining a big workspace. And spoiler alert, as you're scaling anything, you are hitting interesting limits that might have not been obvious to start with. So some context, when I say library workspace, what I mean is a cargo workspace that contains libraries that are all published to Crates.io, right? Like the contrast to that would be a binary workspace like Rust Analyzer, where the main product you're shipping is a binary. You can also split that one up into multiple crates to like benefit from Cargo's parallelization of at compilation time, but you don't have to deal with a lot of the issues like versioning and changelogs and all this stuff because the main product you're shipping is a binary. And that's the one that gets pushed to GitHub releases or something. And also like quick diagram here, like the cargo toml at the bottom is like the workspace manifest is not an actual package. So that's what I mean with a workspace. So the concrete one we're talking about is Rust lib2p. Don't bother if you can't read any of that stuff. It's not the purpose. It's just the idea of showing all the dependencies that we have between the crates in the workspace. I think it's like 32 or something. So I'd say that's a fairly big workspace. And a lot of the things in there get quite complicated, unfortunately. Quickly of why do we actually have so many crates? Well, the idea of the entire library is to be a modular network stack. And so you can swap out like transport protocols, you can swap out multiplexers, encryption protocols for whatever your application needs. And there's built-in modules for DHT, for publish, subscribe, and these kind of things. And so you have crates that represent interfaces, and you can just plug them together the way you need them for your application. So the actual problems that we ran into are some of the things that we've experienced. First topic, continuous integration. So we should obviously all be testing all of our code on every pull request. One of the issues that we ran into was that the cargo doesn't parallelize the test execution across crates. Right? So everything is, if you just say cargo build workspace, it builds things in parallel, but when you then want to test them, it's actually going to sequentially go through all the crates and run those tests. The tests within a crate are run in parallel, but the tests across crates are only run sequentially because they're compiled as individual binaries. So that was an issue because it means if you have 32 crates, they're all going to be compiled in parallel, but then run in sequence and just takes a long time. Second problem was that features are unified across build graphs. That's a good thing while you're using a crate. It's not such a good thing when you're trying to test your crates, because it means that if all of your crates go together into one build graph, features might be activated from different ends. And that could mean that one crate doesn't activate all the features that it actually depends on, but you don't realize it because you have another crate in your build graph that activates the necessary features. So it could be that you're actually releasing something to Crates.io that doesn't specify the correct feature flags of one of its dependencies. The way we solved this was to create a CI job per crate and do that dynamically. So if you aren't familiar yet with the cargo metadata subcommand, it's really useful for this kind of stuff. It gives you a JSON representation of your workspace or of your crate, and you can filter through that with JQ. And this little snippet here is going to give us an array of all the crate names in our workspace. And then we can use that in GitHub Actions to dynamically create a matrix. So we use that JSON, pop it in as an output. And then in a different job, we say, create a matrix from this array. And then GitHub Actions is going to dynamically create one job per crate. And then within that job, you can just say cargo test -- package this particular crate. And so that means this is a sort of no maintenance kind of solution where you can add more crates to your workspace later, and your CI is going to continuously adapt to that. And this means we're testing all of our crates in parallel. We have all the tests run in parallel. We have all the compile times all nicely trimmed down to like 3 to 4 minutes per crate. Next topic is releases and bumping versions. So you'd think, for example, that it's easy to decide what the next version of a crate should be. Well, first, before you do a release, you first have to figure out which one do I actually need to release, right? So if you only have a single crate in your repository, that's easy. You just cut a release whenever you've added a new feature. If you have 32 crates in your workspace, you need to figure out, well, which ones have actually been touched since the last release, and how do I figure that even out? What is the next version? Is the next version a major, minor, or patch? Were there changes in their breaking? All of these questions are really hard to answer when you have to think about so many crates. Again, we've solved this with some tooling. One of the tools that recently appeared on the Rust landscape, which is really great, is cargo assembler checks. Cargo assembler checks uses the JSON representation of Rust stock to tell you whether or not the new API of your crate is Semver compatible with the old one, or whether or not you should make actually a minor or a major version bump based on your current version. So we run that on each pull request, which means as we bump a version in the pull request, we have either a green CI if we're making the correct version bump, or we have a red CI if cargo assembler check says, actually, you've removed a struct from the public API here. This requires a major version bump. So that's really helpful. The second really helpful tool is cargo release, because cargo release can recursively release all the crates that need to be released for pretty much across your entire workspace. Now that's necessary because you know that you can't release a crate unless all of its dependencies are released. So if you would have to figure that one out manually, you would have to sort of like more or less trial and error, see which ones need to be released, and cargo release just does all of that for us. Lastly, a tool we may soon be using is something I'm currently working on, which is called cargo assembler log. Interestingly, as your workspace grows, your changelog file really becomes a source of merge conflicts because many PRs touch the same file. What we would like to move to is to actually add one new file, which contains just that changelog entry, and then gather them at release time into a new changelog. That idea is not new. We just don't have any integration with cargo yet. Breaking changes, another interesting topic. So in the background, you can see one of our milestones. What we actually do with breaking changes is we hold them back up until we think that there are enough breaking changes gathered that it's worth actually merging and releasing them. With a big workspace, what unfortunately happens is that breaking changes kind of scatter through all of your crates. Like if you make a breaking change in one of your leaf crates, sort of like it recursively requires you to make a breaking change to all your others as well. And so we try and hold those back and batch them together to minimize the impact for our users. Lastly, syncing versions across workspace crates. This is a bit of a tricky one and is, I think, one of the most annoying bugs that we've had. So in these two snippets, what you can see here is that we have a package that is on version 0.42.2, and we have another package in our workspace that defines that it needs at least 0.42.0. And it also has a path dependency. And we're all familiar with what this path dependency does. It means that within our workspace, cargo is not going to fetch that package from crates.io, but it's just going to link to it via the relative path. Now, this means if I make a change to my workspace, everything compiles fine. But if I'm now depending on a feature that was only added in 0.42.2, and I release Cademlia, like the bottom package, with 0.42.0, this could break for a user if they manually pin the version. There is an unstable feature flag for compiling with minimal versions, but that's kind of a pain to use as well. And just keeping these versions in sync is really difficult if your dependency graph looks like this. Luckily, we've got workspace inheritance as of Rust 164. With workspace inheritance, we can specify pretty much any key in our manifest, also in our workspaces, and then inherit from that. So for example, we can declare dependencies in our workspace manifest, and then wherever we want to use that dependency, we just say workspace true. This also works for the minimum supported Rust version. This works for your license. This works for pretty much any key that you want to use in one of your workspace crates. If you're not using that and you have a big workspace, I'd highly recommend. It makes things a lot easier. So quickly recap. I've not said this explicitly, but as with many things, it applies. Just try and avoid these problems as long as you can. Like, keep your workspace small. Really think whether or not you actually need that many crates, because it's all complexity that you then have to deal with. Have as many automated checks as you can possibly can. Humans are really good at making errors, so try and avoid that and make sure that anything that you want to have and want to have done is actually enforced in your CI. And write good crate boundaries, or decide on good crate boundaries. One of the most annoying things that we've ran into are breaking changes and how they scatter across multiple crates. So if you scope your crates well into its pieces of functionality, you should be able to avoid a lot of breaking changes that scatter through the code base. That's it. You can find a lot of this code, or pretty much all of this code, in our actual workspace, like the CI checks and the dynamic creation of jobs, or some of the hackery that we've done around cargo metadata and JQ. And you can also check out my Mastodon. I don't post there very often, but yeah, you can follow me anyway. Thanks for listening. If you've got any questions, like, I can't hear you, so if you pop them in Discord, I can read them out and then answer again. Maybe are there already questions? Let's see. I can't hear Lloyd, so somebody would have to type that question into Discord. Are there any major mistakes in libp that are hard to reverse at this moment? I would say mistakes is difficult because in retrospect, yeah, some things should have been done differently. Like, at the moment, there is one crate that pretty much all the other crates depends on, but it's sort of like this. It's this aggregation of, like, these are all the things that everybody needs. Whereas it would have been good to split those into more distinct pieces that are more cohesive, so that not every crate actually depends on that, which would have allowed for avoiding some of these cascading breaking changes. So, like, I think it's also known as, like, if you have a common module or a util crate, like, don't try to avoid this as much as possible. Just have one that has a distinct purpose, and see if you can avoid that all the other crates in your workspace just depend on this one, because any breaking change in that one will cascade through your workspace. So, like, to come back to the question, it has been done like that in libp to start with. I wouldn't say it was a mistake, because those are things you often only learn after you've already committed to that interface. So I wouldn't call it a mistake per se, but it's something we're working on resolving. But breaking up these kind of boundaries is really difficult in retrospect. When are we gonna have a server stable software? Semver stable software. Is that question related to P2P or in general? I'm not sure I fully understand the question. Semver is complicated, yes. Like especially in Rust, because Rust is very explicit about its API, or the crates are very explicit about their API. So the tiniest change can, in theory, be Semver breaking, right? Like even if you have a struct with all of its fields private, you could, in theory, change that for it to suddenly no longer implement the send trait, and that is a breaking change. But the tools like Cargo Semver Check, they detect these kind of things. What did I visualize my package dependencies with? There is a package called Cargo Depth Graph, I think, and that one you just pipe into dot, and then you get this. Graph. Cool. Thanks everyone for listening. Yeah, if you have any other questions, feel free to pop them into Discord. I can answer them afterwards. Thank you.